Hey everyone, welcome to this explainer. Okay, today we're embarking on an absolutely fascinating journey. Have you ever actually stopped and wondered how we take all that messy, brilliant, abstract logic bouncing around inside our brains and somehow translate it into the exact, rigid syntax that a computer can actually understand? Well, that, my friends, is the magic of algorithms. We're going to break down the ultimate blueprint of how human thought becomes machine code, moving all the way from high-level problem solving right down to the specific grammar you need to write it all out.
All right, let's dive into this. Here's our roadmap for today. We're going to start with the algorithm foundation, then look at 3 ways to write it, dive into pseudocode basic grammar, explore logic and variables, and finally, we'll wrap up with controlling the flow.
Okay, moving right along to Section 1, the algorithm foundation.
Now, before we can even think about typing out a single line of code, we desperately need a solid conceptual foundation, right? We have to know exactly what it is we're trying to build. So, at its absolute core, an algorithm is simply a step-by-step process of solving a particular problem. Honestly, think of it like a highly logical recipe. You've got a starting point, you have a desired outcome, and the algorithm is just the exact sequence of instructions you absolutely must follow to get from point A to point B, without any confusion whatsoever.
You know, what's really interesting about this is a quote from our source material that perfectly frames the concept. It says, "Algorithm is an expression for a program." I just love this framing because it shows exactly how an algorithm acts as a vital bridge. It's that crucial intermediate step between identifying a real-world problem and actually writing the final executable software program. It's literally pure logic, expressed perfectly before the machine takes over the heavy lifting.
But here's the catch. To be considered a true algorithm, it can't just be some loose, wishy-washy set of ideas. There are 5 absolute conditions that give an algorithm its structural integrity. Every single algorithm must have input, output, definiteness, finiteness, and effectiveness. These are the strict rules of the road, guys. If you're missing even one of these 5 conditions, your step-by-step process is basically just going to fall apart the second you try to turn it into a working program.
Which brings us to Section 2, 3 ways to write it. So, once we have those 5 rigid conditions locked in our minds, how do we actually express them out in the real world? Like, how do we get them out of our heads and onto paper? Well, there's kind of an evolution of communication here. First up, we can just use natural language, English, literally just writing out a simple step-by-step process using the everyday words we're using to chat right now. Second, we can step it up and use a flowchart. This is a graphical representation of the problem statement, where we use shapes and arrows to visually map out the logic. And third, we land on the pseudocode approach. When it comes to the design and analysis of algorithms, pseudocode is absolutely crucial. It's the specific, formalized method we use right before implementing the actual code, and, spoiler alert, it's what we're going to focus on for the rest of this explainer.
All right, let's open the dictionary for Section 3, Pseudocode Basic Grammar.
So just like learning any new language, pseudocode follows some very specific rules to ensure absolutely everyone can read and universally understand the logic. And this brilliantly illustrates the difference. In natural English, you might just casually write, "Start the algorithm name sort." But in pseudocode, we use a very uniform structure. It always starts with the exact keyword algorithm, followed directly by the name of the algorithm, and then finally the parameter list right there in parentheses. It's clean, it's totally uniform, and it instantly tells the reader exactly what they're looking at. Building on that thought, let's quickly punch through 3 foundational grammar rules that dictate the visual look of our code. First, just like standard coding, identifiers, the names we actually give things, must always begin with a letter, no exceptions. Second, if you want to leave a little note for yourself or another human reading the code, comments always begin with double slashes and just continue until the end of that specific line. And finally, when you have a block of statements that belong together as a family, they are neatly enclosed in open and closed curly braces. This simply gives our logic a really clear, organized physical structure on the page.
Moving right along to Section 4, Logic and Variables. Okay, so now that we know how to set up the document itself, let's look at the actual mechanics. This is how pseudocode stores data and compares information. In standard math, saying A equals 5 is just a statement of fact, right? But in pseudocode, we are actively doing something. So the crucial point here is that we use a colon and an equal sign together to explicitly command the computer, hey, assign this value to this variable right now. And notice, we always finish the statement with a semicolon.
We also have very specific terms for taking in data and spitting out results. If you've ever dabbled in traditional C code, you might already know the functions scanf for input and printf for output. Well, in our pseudocode equivalent, we keep it incredibly readable and conversational. We literally just use the word read for input and write for output. Makes sense, right? And when we need to compare Boolean values, we just stick to standard relational operators, things like less than, greater than, or equal to, and so on.
Oh, and just a really quick syntax note here. When you're storing multiple data points together in a single list, what we call an array, you always use opening and closing square braces to access them. It's a tiny rule, sure, but it is absolutely vital for keeping our data perfectly organized.
And finally, we arrive at Section 5, controlling the flow.
Look, having variables is great and all, but the true, real-world power of an algorithm, the whole thing that makes it dynamic, is its ability to make decisions and repeat tasks completely automatically. Let's take the while loop as an example. Basically, while a condition remains true, do these statements. Think of it exactly like your morning alarm clock. While the snooze button is pressed, do sleep for 5 more minutes. But as soon as that condition becomes false, it immediately stops and just pops right out of the loop.
Let's move on and see how this builds with our next structure, the for loop. You use this one when you know exactly how many times you want a task to repeat. The syntax is pretty straightforward. For a variable assigned to value 1, to value 2, step, do. Now what's really important to catch here is that step parameter. It tells the loop exactly how to count. It can take an increment operator to count up or a decrement operator to count down through your data.
We also have a slightly different loop structure called the repeat until statement. Honestly, this one does exactly what it sounds like. It'll repeat a block of statements over and over again until a specific condition becomes true. The cool thing here is that it guarantees the code runs at least once before checking if it should stop.
Now beyond loops, we have conditional statements for making choices. The if-then-else statement is basically a simple, binary fork in the road. If a condition is true, then execute statement 1. Else, meaning if it's false, drop down and execute statement 2 instead. It's super simple but incredibly powerful, giving your algorithm a direct, clear choice between two paths.
But, hey, what if you have a massive intersection with multiple roads, instead of just a single fork? Well, that is exactly where case statements come in. It acts a lot like a switch. You list out multiple conditions. If condition 1 is true, do statement 1. If condition 2 is true, do statement 2. And it goes all the way down the list until it finds a true statement, usually wrapping up with a default else statement just in case literally none of the specific conditions were met. It's a highly efficient way to route really complex logic.
Okay, wow. We have covered the foundation, the formats, and the precise pseudocode grammar you need to actually translate human thought into a structured blueprint. So I want to leave you with this final, practical thought to really test what you picked up today. If an algorithm is an expression for a program, how would you write a pseudocode block for your daily morning routine? Seriously, think about your read and write inputs, your while loops for hitting that snooze button, and your if-then-else choices for breakfast. Start mapping out the logic of your everyday world, and I promise you'll be writing flawless algorithms in no time. Thanks so much for joining me on this explainer, and keep exploring.